Hello students, this begins a video on the basic properties of liquids and solids, our introduction to chapter 12. The objectives of this video are to compare and contrast the properties of liquids and solids to allow you to be able to compare, contrast all the three states of matter, and explain and apply some new terms: viscosity, entropy, surface tension, capillary action. You should be able to, after this video, to compare and contrast properties of liquids and solids and complete a chart very similar to this. You should be able to answer a little more specific of questions about the properties of solids, liquids compared to gases, or complete something like a Venn diagram comparing. At the end of the video, I will share my answers to these questions so that you can test yourself on your understanding of this information. So how exciting! How exciting after 2 chapters with gases that we get to move on to liquids and solids. But where do we start? With the kinetic molecular theory. So remember, the kinetic molecular theory of gases was very specific. But as far as the other states of matter, we're really just asking, how do the particles in that state of matter move? Kinetic, of course, energy of motion. And then understanding that, we can explain the physical properties that are associated with our different phases, or even compare different examples of liquids, different examples of solids as far as their physical properties. So we've gone over a lot already this year. So I'm just going to begin by just very quickly going through some slides. So we know a characteristic of a liquid is that it has a definite volume and an indefinite shape. They are fluids and they have the other properties that I've identified here. But we know kind of the most outstanding property of a liquid is that the kinetic energy and particle attraction are balanced, so that the volume is limited because the particle attraction does not allow the particles to fully expand to fill their container like a gas. But yet they have enough kinetic energy that they don't have a set shape, indefinite shape, similar to a gas and different, of course, from a solid. Here are just another list of properties that we know that we associate with liquids. We'll talk much more about solution formation to come. Now, of course, liquids can behave as solutes, but also solvents. They can be dissolved, but they can also be the dissolver in the creation of a homogeneous mixture. All right, so let's get into some unique properties that liquids show us. So I'm sure that you've talked about surface tension before. Surface tension is a result of the liquid molecules exerting attraction on each other, or liquid particles, I should say. Now, we know that in a liquid particle is going to be pulled by particle attraction by all surrounding it, and it will pull back. However, the ones at the surface, they are only pulled to the side and downward. So what that does is creates a tightening at the surface. Imagine pulling on a piece of saran wrap or a Ziploc bag. That's what these particles are doing to the surface particles. That allows the surface to be able to hold more weight than it would otherwise, like being able to support a water bug on the surface of a puddle. This also explains why a lot of liquids form droplets. They are being attracted and pulled sideways and down at the surface. So what that creates are shapes that maximize touching and minimize surface area. So that's how we get these beautiful, beautiful drops, of course. There are different definitions of surface tension. But again, it's because of the cohesive, because of the particles pulling and pulling on each other at the surface. And so one definition I found talks about that leads to the smallest possible surface area. But we understand that allows force to appear a strength that then can support more weight than could otherwise. All right, that's surface tension. And different liquids show different degrees of surface tension based upon the strength of their particle attraction. I'm sure we've all cleaned up a spill with a paper towel. But I'm also sure that we've seen when we place a straw into a liquid, some of the liquid climbs up the straw before we even put our mouth to it. That's capillary action. Capillary action is defined as the movement of a liquid up a narrow tube. The narrower the tube, depending upon the degree of attraction between the liquid and the material the tube is made out of, can deliver different levels of this rise. Now this is interesting, and we'll come back to this to talk about this. Okay, so we have adhesion and cohesion. So cohesion, for example, in these water molecules, is the attraction of like molecules to each other. So one water molecule attracting force on another water molecule. However, particles can also show adhesion. You can have attraction between different substances. So if we could imagine going microscopically where the liquid is meeting this tube, if this is the wall of the tube, this would be the water molecules trying to not only exert attraction on each other, but also to attract and come into contact and get closer to the material of the tube. It must be of like chemistry. So do you see kind of what happens? These molecules work together and they end up kind of creating a stack where they help each other to not only attract to each other, but also to the walls of the vessel. So again, the narrower the tube, the greater the rise that we'll see. Now, in the case of mercury, mercury is much more attracted to itself than it is to glass and plastic. So it creates what we call a reverse meniscus. So we don't see any adhesion there like we're seeing with the water. And as I mentioned, that's why a menisci form. All right, another property. Viscosity. Viscosity is a liquid's resistance to flowing. I'm not sure exactly what these liquids are. I bet this might be honey, which we say is thick or it pours slowly. Well, that's because of the difference in viscosity between the particles that are present in honey versus this is probably just food coloring in water. So in comparison, water is less viscous. Now they wouldn't be a liquid unless there was particle attraction, but if this is pouring more slowly, it's of greater viscosity. The particles are resisting exchanging places because they're so attracted to each other. So we usually talk about viscosity when we're comparing liquids. So this is a graphic that compares water with milk and oil and syrup, heavy syrup, chocolate syrup. We could add ketchup to this and so on. So we know different liquids have different flow rates. Well, we could call that and explain that through viscosity. They have different viscosities and it's all based upon particle attraction. All right, some properties of solids. So I'm just going to list these and show these because we've talked about these a lot already. So we'd say they have low kinetic energy, that particles are locked in place, but they do vibrate and rotate. But here's a new term for us, entropy. Entropy for our purposes, can be synonymous with disorder. So if we just picture a gas with all that chaos, we'd say that gases have very high entropy. Entropy, we'll talk much more about in second year chemistry, is symbolized by a capital letter S. We don't have to know that right now, just that this term means disorder. So a gas has just random, very high kinetic energy. A gas would have the highest entropy, where of the three states of matter, a solid has low entropy. Other properties of solids. All right, so ladies and gentlemen, could you check the same set of properties that I have checked? So if you want to pause and take a look at this a little deeper, I'll move this up. And if you saw on the video, it's incredibly interesting, but solids do show diffusion, particularly if two metals are together under pressure. What we measure is that some of the cations in one of the metals migrate over into the other metal, and we get some mixing. So it's understanding that with pressure, the molecules, because they're vibrating and they rotate, that sometimes they can switch positions, especially under pressure. But that's very, very slow. We would call only solids to be hard. Now, just to review this term, because it'll come up in the next couple of videos. Hardness is a substance's resistance to breaking. The harder the substance, the more force you have to exert on it to break. Now, to call something brittle, that just means when you exert pressure on it, it will break into pieces like glass. The opposite of brittle is malleable. So when you exert force on a metal, we know it molds. But something like a piece of sodium chloride, if you hit it with a hammer, it's going to break into a bunch of pieces, just like glass would. So if you exert a lot of force to break it, it's hard, but if it breaks into pieces, it's brittle. If it breaks easily, it's soft. So soft does not mean squishy, like a marshmallow or like a stuffed animal. It just means it's easily broken. All right, here would be another set that we should be able to answer. We'll talk much more about how the particle attraction dictates the specific properties. Remember, whenever we're asked these questions, we're definitely under the assumption that gases are ideal, so we ignore their particle attraction. And could you create the same comparison? So solid and liquid share these properties, but are different in these. Okay, that begins our journey of chapter 12.